All right, guys, so today we're doing cubic transformations. Now, what is a cubic? It is a function that has a leading term whose power is 3.
That's what we meant.
Okay, so on the front, I didn't copy over what the front looks like, but on the front of your notes there where it says cubic parent function, go ahead and put f of x is equal to x cubed. That is our parent. Oh, that doesn't show up very well for you guys. That is our parent function. It's called a cubic. It's a cubic function. So let's go ahead and we're going to graph it. We're going to graph y equals x cubed. Now, what makes the parent function a parent function? What's special about it? It hasn't been what? Changed at all. What are the changes that could happen to it? It could be stretched or compressed. It could be translated, and it can be reflected. So none of those things have happened. Where is our central point? The origin, 0, 0. Now on a cubic function, this central point has a special name. Does anyone know what it is? It's not the vertex anymore. Inflection point. It is literally on the notes right there. Inflection point. Now, we know our x is being cubed. So if my x value is 1, what is my y value? What is 1 cubed? 1, right? 1 times 1 times 1 is 1. So our next perfect point is 1, 1. What if my x value is 2? What is 2 cubed? 8, right? 2 times 2 times 2 is? So I go over 2 up 8. So this is starting to look like half of a what? Quadratic. Now here's where it gets different. If I go over -1, what is -1 cubed? -1. So now it clearly is not a quadratic. And what is -2 cubed? -8. So a cubic function kind of does like an S-curve thing. It's hard to draw. Ugh. Wow. Okay, that's as close as I can get. So this is the line y equals x cubed. Notice, how many solutions does it have? This parent function, how many solutions? What's another word for solution? X-intercepts? 1. There's only 1. On this function, there's only 1. Now, over here, our parent function equation is f of x equals x cubed. Now, we're going to do domain and range, and we're going to do the set and interval notation for both. So domain is our what values? X values. Now, in my head, I still do this. Every single time I'm going to find domain and range, I ask myself what's the least value and what's the max value. So on the x-axis, what is my least value that this graph goes to? -infinity. And what is the max value? Infinity. Or in other words, All real numbers. Very good. So if I'm trying to write this in set notation is what notation? With the squiggly brackets. Set squiggly, set squiggly, set squiggly, right? Set squiggly. So I start off with my squiggly bracket, and then what do I write? X is an element of, yeah, very nice. This epsilon E means is an element of. All real numbers. And squiggly. Oh, that's really small for you. There we go. Is an element of. And then I prefer myself interval notation because it works how my brain works, right? I ask myself, what's the least value and then what's the max value? Interval notation goes the exact same way. What was the least value? Negative infinity. Can I touch it? So what do I put? Parenthesis. What's my max value? Infinity. Can I touch it? Parenthesis. We always go blank to blank. Least to greatest. Least to greatest. I have to say that because there are still people in here that are flipping these. They'll put 2 comma negative infinity. Negative infinity is the lowest possible number ever. It should never be on the right. Ever. Okay? So then range. What is my least range? My least y value? Negative infinity. And what's my max y value? Oh, or in other words, all real numbers. So how do I write that in set notation? Squiggly y is an element of all real numbers. And what was my least value again? And my max value. Guess what? Cubics will always have all real numbers for both domain and range. Domain and range always have all real numbers. Always for cubics. Always, always, always. Cubics have all real numbers. Okay. So on this parent function, where was our inflection point? 0, 0. Where is our x-intercept? 0, 0. If this problem hadn't been so nice and easy, how would you find the x-intercepts? What do you have to do to find the x-intercepts? To what? To y. So if your y has a 0, how would you solve, say, a quadratic? So you have 0 is equal to x squared plus 3x plus 4. How would you find that x-intercept? Oh my gosh, you have to solve it. When you're trying to find x-intercepts and they're not so nice, you have to solve the cubic. What about y-intercepts? How would you find the y-intercepts if it wasn't so nice a problem like this? Do the same thing except what? Plug 0 into the x. Plug 0 in for x. But this time it's so much easier because you can just do what? And just simplify it. So on the x-intercepts, you would have to solve it, factor, quadratic formula, whatever. On the y-intercepts, you have to plug 0 into x and simplify. What is the y-intercept for this problem? 0, 0. Now, end behavior isn't just specifically for cubics, but we decided to go over it today anyway. When I'm talking about end behavior, I'm talking about where the graph ends up. So, for example, here if I'm going to the left, where does it end up? Going down, right? If I'm going to the right, where does it end up? Going upward. So are they going in the same direction or opposite directions? Opposite, good. When I'm thinking about a quadratic, like so, am I going to the left? Which way am I ending? Where is my end happening? Upward. If I'm going to the right, where do I end? Up. So my end behaviors are going the same direction or opposite? Same. What about a linear? If I'm going to the left, which way am I ending? Down. If I'm going to the right, which way am I ending? So quadratics had the same end behavior. Linear had opposite end behavior. And cubics have same or opposite? Opposite end behavior. Does anyone see the pattern? Anyone want to take a guess? Yes, Sam?
Odd exponents are in opposite directions, and even exponents are in the same.
Wonderful. Look at the exponents. Here, this is odd or even? Even. So it has the same end behavior. This exponent, there's an invisible what? 1. It is odd, so it has opposite. 3, is that odd or even? Odd, so it has opposite. What would x to the 4th? What would that be? Same end behavior. What about x to the 5th? That would be what? Opposite. Yes. You can think odd, opposite. Odd, opposite. They both start with O, right? Odd, opposite. So over here in our notes, end behavior, you look at the exponent. You look at the exponent. If it's odd, what is our end behavior? Opposite. Odd, opposite. If it's even, what's our end behavior? The same. So if I had x to the 57th power, is it an odd or even function? It's an odd function, meaning what's my end behavior? Opposite. So that graph to the 57th power would look like that, with some crazy amount of loops in the middle. Anyway, we're never going to go that high, ever. We'll probably never go past 6 or 7. But anyway, before we go on to the actual transformations, let's go over what a relative and local maximum and an absolute or global max are. So looking at this left picture here, and I'm telling you that it has a relative or local maximum, how would you explain what a relative local max is?
Maybe the highest point that is a set point.
I know it's hard to describe. Is it our overall maximum point? Is it the maximum point on the graph? No, because why? What do you notice? It keeps on going up infinitely there, right? So locally, It is our maximum point. It is like a peak of your cubic function here. So we call this a local max. What about this? What would we call this point down here? It is a local min. It's not our minimum point because the graph keeps on going down as its end behavior there. So we can't just call it a minimum anymore. It is a local min. Now the reason why it says relative / local is because there's multiple names for it. Some teachers call it a relative min, some teachers call it a local min. I've always learned local, so that's what I go with, but it's also called a relative. Now over here, how could you explain an absolute or global max? Yes, it is the highest point on the graph overall. Nothing else goes higher than it. We call it a global or absolute max. So, what are the only types of functions that could possibly have an absolute or global max? What else now, though? Even functions, right? Because even functions have the same end behavior. So this function could have a global or absolute minimum point. Global min. Right? It will have an absolute minimum point. Will it have an absolute maximum point? No. Why not? It continues upwards on both sides over there. So it will have a global min, it won't have a global max. We do not go that in depth on this. Pre-cal goes way more in depth. You'll see this a lot in pre-cal. I know Miss D said that all the time. I'm so sorry. But really, for sure, this you'll see a lot, okay? All right, so over here, does this look familiar to you? Why? When did we use something like this before? For what? Quadratics. What else? We also saw this in absolute value. This function helps us determine what transformations are happening. So I like to call this thing the transformation function. Okay? All of the letters have remained the same no matter what the function is. So you've seen it in absolute value, you've seen it in quadratics, and now you've seen it again in cubics. Now this is the very first time that I'm teaching it to you, so I'm still going to show you what each letter means, but from now on I will never again tell you what each one of these letters means because it remains the same throughout the year. Nothing will ever change except this number, right? Okay. What does A do to the function? It can reflect it. It can reflect it. What else can it do? Stretch or compress it. And it is always the blank transformation. Starts with a V. A V. A V. Vertical. Yes, it is the vertical. Not B. Yeah. V. It is the vertical. Now, I highly recommend you write small here. We're going to write a lot in these spaces. They're not big enough, okay? So this is the vertical transformations. If A is negative, what happens? It's reflected over what? Now, either you can say vertically reflected or you can say reflected over the x-axis. Either one is perfectly correct. I prefer to say it's vertically reflected, but that's personal preference. Yeah, that's on the last line. If your A is a whole number or bigger than 1, what do we say? It's a stretch. What if it is less than 1, meaning like a fraction or a decimal? It is a compression. Now, does anyone know why I just put absolute value symbols on those A's? Yes, because the negative does not affect these values at all. If it's a negative, it means it's what? Reflected. So for example, what would we say if the A value was a -3? What transformation is happening? It's a vertical stretch by 3, and it's also a, yes, a vertical reflection or a reflection over the x-axis. That's all the vertical transformations that can happen for A. Now, you haven't done very much with B. We're going to do a little bit more in this unit. B is the what transformations? The horizontal. Yep. B is the horizontal. Now, is your B being cubed? Yes, it is being cubed, meaning it is inside of our set of parentheses. Anything that is inside of the parentheses is what? You all mumbled, I couldn't hear it. Maybe you're not saying it? Inside the parentheses, like the H, is always what? Opposite, backwards, tricky. However you want to remind yourself. Same thing with B. It is opposite or backwards. I like to think backwards. I know Miss D did tricky, but I do backwards. So, knowing that B is backwards, if B is greater than 1, what do we call it? It's a compression. Now, not only is the verbiage backwards, the number is also backwards. So it's a compression. Now say B was 2. We would say it's a horizontal compression by, do you know how much? 1/2. It's the reciprocal. 1/B. By 1/B. So for example, if we had a 3 there, you would say it's a horizontal compression by 1/3. Now, if B is less than 1, what do we call that? It's backwards, so it's a stretch. So, for example, if your B value is 1/2, it is a horizontal stretch by 2. It's the reciprocal. It's still technically 1/B. Do you need me to explain why it's still 1/B? Okay, so if I have a half, right, you would say that it's the reciprocal 1/B or 1/1/2. How do you simplify this? Anytime you're dividing by a fraction, what are you actually doing? Multiplying by the reciprocal of the denominator. So 1 times 2/1 is what? 2. You don't need to remember all of this. Should you probably know this? Yes. It's especially going to come in handy when we do rational functions. But for now, just remember it's the reciprocal. Now, if B is negative, what does that mean? It's reflected, this time over which axis? Did you guys know that about anytime you're dividing by a fraction, you're just multiplying by the reciprocal? We're going to have a tough time in rationals. That's next semester, though. We don't need to worry about it now. All right. Now, Back to the easy peasy stuff. H, what do we call H? It is our what? What does it do to the graph? Horizontal translations. Yes, horizontal translations. So, if H is negative, where does it go? To the right. If H is positive, where does it go? To the left. What about K? What does K do? Vertical translation. What's that, Josh? You what? Oh, okay. If K is negative, where does it go? What? Whoa. If K is negative, where does it go? Down, yeah. I almost wrote left. I'm like, yeah, it's left, yeah. If K is positive, where does it go? Wonderful. And then where is our inflection point? In terms of A, B, H, and K. Where is the inflection point? HK. Wonderful. And then end behavior is exactly what we just learned. It is determined by the what? Yes. Determined by the exponent. So if you've ever heard of an odd or even function, an odd or even equation, it's just referring to the exponent. So if it's an odd exponent, oh my gosh, it's an odd function. If it's an even exponent, it's just an even function. Any questions on any of these notes? Pretty straightforward, right? All right,